Hey everyone and welcome back. Today we're diving deep into a really cool area of science.
Yeah.
Photocaged compounds.
Photocaged compounds.
It's like they're just waiting there, like a
Right.
molecular time bomb.
Yeah, it's really amazing. We can actually control when and where a reaction happens just by shining a light.
Exactly. It's like a dimmer switch, but instead of controlling the brightness,
Yeah.
we're controlling the molecule's action itself.
Yeah.
So for our listeners out there who haven't encountered this before,
Uh-huh.
how do photocaged compounds actually work?
Well, think of it like this. You have this molecule, the one that's going to do something really cool,
Right.
but it's attached to this other thing, a photoablative group.
Okay.
And that group, it acts like a cage, basically, keeping that active molecule all locked up
Uh-huh.
until we hit it with a very specific wavelength of light.
So it's like a jailbreak, but for molecules.
Exactly. That's a great way to put it.
And it's all triggered by light.
Yeah, that burst of light.
Wow.
It makes that photolabile group break apart,
Okay.
and then that releases the active molecule to do its thing.
So what makes that so groundbreaking? Why should we care?
Well, think about neuroscience.
Okay.
We can use this to look at how neurons communicate,
Uh-huh.
how our memories form,
Right.
even how diseases affect the brain.
Yeah.
It's like shining a spotlight on how our minds work.
Wow, that's powerful stuff.
Yeah,
We also mentioned drug delivery earlier.
right.
How do photocage compounds help with that?
So imagine a drug that only becomes active when it reaches its target, like a tumor. That's the promise of these compounds.
Okay.
Keep it inactive until it's exactly where it needs to be.
Right.
Minimize side effects.
Yeah.
Maximize effectiveness.
Like a laser-guided missile.
Exactly.
It's incredible,
Yeah.
designing these things.
Yeah.
It can't be easy, can it?
It's definitely a challenge. Scientists really need to understand both photochemistry, which is how light interacts with molecules,
Right.
and functional molecular engineering,
Okay.
which is basically designing molecules to do very specific tasks.
So it's like a delicate dance between light
Yeah.
molecules and engineering.
You could say that, for sure.
Mm-hmm.
Scientists are always working to make them more efficient, more stable, more targeted, and
Okay.
progress is really remarkable.
This is pretty high-tech even for us.
Yeah,
Can we break this down for everyone listening and
sure.
maybe talk about some real-world examples?
Absolutely. Let's start with neuroscience.
Okay.
Researchers are using this tech to look at the activity of individual neurons.
Okay.
They can basically uncage neurotransmitters
Uh-huh.
right at the synapse, that little gap between neurons.
Yeah.
And this allows them to study how signals are transmitted in the brain.
So it's like they can watch those brain cells talk to each other in real time.
Exactly.
That's incredible.
Yeah.
What about drug delivery? You mentioned cancer therapies.
Right. So picture this.
Okay.
A photocaged chemotherapy drug injected into the body,
Yeah.
and it just circulates harmlessly until it reaches that tumor site.
Hmm.
Then doctors use a focused beam of light
Wow.
to activate the drug,
Right.
and that releases its cancer-killing power right at the tumor.
That's so much better than traditional chemo,
It is.
which can also hurt healthy cells.
Yeah, exactly.
This is incredible.
It is. And while this is all still pretty early,
Yeah.
the potential benefits are huge.
Yeah.
Reduce side effects,
Oh.
more effective treatments,
Yeah.
maybe even curing diseases we once thought were incurable.
This is pretty mind-blowing stuff.
I know.
I feel like we're on the edge of something big here.
Definitely.
But can we bring it back to basics a little bit for everyone listening
Uh-huh.
and talk about the different types of photocaged compounds
Okay.
and how they're actually made?
Of course, there are so many different kinds,
Yeah.
each one made for a specific purpose.
Mm.
And the design process is really quite fascinating.
Okay.
It starts by choosing the right photolobular group.
Yeah, that light-sensitive cage.
Exactly.
So it's not a one-size-fits-all kind of thing.
Not at all. No.
Okay.
It depends on a bunch of factors,
Okay.
like what kind of light you want to use,
Uh-huh.
how quickly you need it to break apart,
Right.
and even where the compound will be used.
So it's like you're building a custom suit of armor for the molecule
Yeah, that's a great way to think about it.
with a weak spot just for light.
That's it. And once we have that figured out,
Yeah.
then it's all about attaching it to the active molecule,
Yeah.
the one that's going to do all the work.
Right.
And this is where we need some serious molecular engineering skills.
Okay.
You have to make sure it doesn't interfere with the molecule's function
Hmm.
and that the whole thing is stable and safe to use in living things.
Sounds like a delicate balancing act.
It definitely is.
Getting it all just right.
It is, and that's what makes it so exciting.
Yeah.
It's constant innovation, pushing the boundaries of what's possible with chemistry and light.
I'm impressed. But can we see a few more examples of
Sure.
how this tech is being used in different fields?
Absolutely.
I'm sure everyone listening is eager to hear more about what it can do.
Yeah, for sure. You're right. There's a ton of applications out there.
So many.
Let's go back to neuroscience for a minute.
Okay.
One really cool area is optogenetics.
Optogenetics? I've heard that word before,
Yeah.
but honestly, I'm not totally sure what it means.
Okay, so optogenetics is
Yeah.
basically using light to control the activity of cells,
Okay.
specifically neurons that have been modified to be light sensitive.
So you're saying we're engineering brain cells that
Yeah.
respond to light.
Exactly.
That sounds like science fiction.
I know, right?
Wow.
But it's actually happening in labs all over the world.
That's incredible.
Yeah, and photocaged compounds are a huge part of it.
Okay, I'm intrigued. But how do they actually fit in?
So imagine this.
Okay.
You have a neuron that's been engineered to express a light-sensitive protein, and we attach a photocaged neurotransmitter to it.
Okay.
Now, when we shine light on that neuron, the cage breaks apart
Right.
and releases the neurotransmitter.
So it's like a two-step thing.
Yeah, exactly.
Light triggers the protein,
Yeah.
and the photocaged compound is the signal
Exactly.
that makes the neuron fire.
That's a great way to put it, and the level of precision is amazing.
Wow.
Researchers can actually target specific types of neurons in very specific parts of the brain.
So we basically have a remote control for the brain.
Kind of, yeah.
I can only imagine what that means for understanding how it works.
Right.
And maybe even treating diseases.
Exactly. Optogenetics has a lot of potential for things like Parkinson's, Alzheimer's, even chronic pain.
That's amazing.
It is.
We could treat these conditions with light.
Yeah, potentially.
Let's not forget about drug delivery, though.
Right, of course.
I want to hear more about targeted therapies.
Okay, so one area where this is really taken off
Yeah.
is in treating inflammatory diseases like rheumatoid arthritis.
Rheumatoid arthritis is tough to treat.
It is.
I know from our past deep dives that the medications have a lot of side effects.
That's right, and that's where photocaged compounds can help.
Okay, how so?
So imagine injecting a photocaged anti-inflammatory drug right into the affected joint.
So instead of taking a pill that affects your whole body,
Yeah.
you're going right to the source.
Exactly, and then you shine a light on the joint and activate the drug only where it's needed.
Wow. That minimizes the side effects.
Exactly.
This is a game changer for people with these conditions.
Absolutely.
It's amazing to see how this technology is helping people.
It really is.
All this talk about photocaged compounds is making my inner science geek come out.
I get it.
I want to know more about how they're actually made.
Okay, well, it all starts with choosing the molecule you want to cager. Like a drug, a neurotransmitter, or another signaling molecule.
So you pick the main ingredient first?
You got it. Then you choose the right photolabelable group.
That light-sensitive cage.
Yeah, and there are a lot to choose from.
I bet each with its own special properties.
That's right. Scientists have to think about the type of light they want to use,
Okay.
how quickly they need the cage to break apart,
Right.
even the environment where it'll be used.
So it's like finding the perfect match.
Yeah, you could say that.
Between the cage and the molecule.
Exactly. And then once you've found that perfect match,
Yeah.
that's where the real molecular engineering comes in.
Okay.
You have to make sure it's attached securely, but it doesn't mess with how the molecule works.
That sounds so complex.
It is.
Wow.
It takes a lot of expertise, but it's so cool.
Yeah.
Because it brings together all these different scientists,
Yeah.
chemists, biologists, engineers,
Uh-huh.
all working to create these really precise tools.
It's amazing.
It is.
But what are some of the challenges that come up?
Well, one of the biggest is light penetration.
Oh, right. We talked about that before.
Yeah.
Light doesn't always reach deep into tissues.
Exactly. So if you're trying to activate something deep inside the body, it can be tough.
Like trying to shine a light through a forest?
Yeah, that's a great way to think about it.
Wow.
And this is especially important for things like cancer therapy,
Right.
where you need to get to those deep tumors.
So how are scientists working on that?
Well, there are a few ways.
Okay.
One is using nanoparticles that can carry the photocaged compound deeper into the tissues.
Like tiny delivery trucks.
Exactly.
Wow.
Another way is using two-photon microscopy,
Okay.
which uses longer wavelengths of light that can penetrate further.
So instead of a flashlight, you're
Yeah.
using a laser beam.
Exactly. But light penetration isn't the only challenge.
Okay, what else is there?
Well, another one is making sure these compounds are stable.
Okay.
We don't want those cages opening up too early.
Right, before they reach their target.
Exactly. So it's a balance between stability and sensitivity. We want it strong enough to hold the molecule, but sensitive enough to break apart with the right light.
Got it. And then there's also safety, right?
Absolutely.
Biocompatibility.
Yeah.
We want to make sure these compounds don't hurt healthy cells.
Exactly. Safety is always a top priority.
Of course.
So it takes a lot of testing to make sure they're effective and safe.
It sounds like there's still a lot to do.
Yeah.
But the progress is really impressive.
It is.
I'm really excited to see what happens next.
Me too. It feels like we're just getting started.
It does.
There's so much more to explore.
Okay, so we've talked about how photocaged compounds work,
Uh-huh.
the science behind them,
Right.
and even some really cool ways they're being used in neuroscience and medicine.
Yeah, it's pretty amazing stuff.
But what does it all mean for the future?
I think it's a real game changer.
Okay.
We're moving from a place where we had limited control over these biological processes
Right.
to a place where we can manipulate them with incredible precision.
Wow.
Imagine a future where we can turn genes on and off at will,
Yeah.
deliver drugs exactly where they need to go,
Uh-huh.
even repair damaged tissues with light.
It sounds almost too good to be true.
I know, right?
Like something out of science fiction.
But that's the beauty of science.
Yeah.
It's always pushing the boundaries of what we thought was possible.
So where do we go from here? What are some of the most exciting things on the horizon?
One area that I'm really excited about is photocaged antibiotics.
Okay.
We're facing this growing threat of antibiotic resistance.
Yeah.
And this technology could really help us fight back.
Yeah, I remember reading about that.
Mm-hmm.
The idea is to create antibiotics that only become active where the infection is.
Exactly.
So you're minimizing the harm to healthy bacteria
Right.
and reducing the risk of resistance developing.
That's it. And think about what that means
Yeah.
for treating chronic infections.
Right.
Or even preventing infections in the first place.
That's incredible.
It's a whole new way of thinking about antibiotics.
Wow. And what about beyond medicine?
Yeah.
Are there applications in other fields?
Absolutely. In materials science, for example.
Okay.
Researchers are using photocaged compounds to create self-healing materials.
Self-healing materials.
Yes.
So like a bridge that can repair its own cracks.
Exactly.
Or a phone ring that fixes scratches with light.
That's the idea.
That's straight out of a movie.
It is.
But I can see how that would be revolutionary.
It would completely change so many industries.
Yeah. And what about environmental science?
Well, there too.
Hmm.
You could use photocaged compounds to make solar cells more efficient.
Okay.
Or break down pollutants in a really targeted way.
It's amazing to think about the potential
It is.
across so many different fields.
It really is. It's like this ripple effect.
Yeah.
One innovation leads to another.
But with all this power comes responsibility, right?
Absolutely. We need to be really careful
Yeah.
about the ethical implications as this technology develops.
Especially in neuroscience.
Right.
Like we talked about earlier.
Yeah.
The ability to control brain activity so precisely
Uh-huh.
raises a lot of questions about free will privacy and the potential for misuse.
Exactly. Those are really important conversations to have.
Absolutely.
We need to make sure this technology is used responsibly,
And ethically.
right? It's like we're exploring a whole new world.
Yeah.
We need to be bold,
Uh-huh.
but also cautious.
Yeah. I like that.
Embrace the possibilities,
Right.
but acknowledge the risks.
I think the key is transparency,
Absolutely.
open communication,
Yeah.
scientists, policymakers, ethicists, the public.
Everyone needs to be involved.
Well, I hope our deep dive today
Yeah.
has given everyone a good look at this incredible technology.
I hope so.
Photocage compounds are still in their early stages,
Right.
but the possibilities are really amazing.
It's been great exploring this with you.
Likewise.
And with everyone listening.
So to all our listeners out there,
Yeah.
thanks for asking questions, stay curious, and let's see where the light of scientific discovery leads us.
That's what it's all about.
Until next time, keep exploring.